We begin by collecting pairwise preferences from an LLM using a forced choice paradigm. Basically, a bunch of queries which represent two distinct textual scenarios. For example, asking the model, you receive $5,000 bonus or you receive a pet parrot, which do you prefer? By repeating this process for hundreds of outcome pairs, we can build a preference graph in which each node corresponds to a potential state of the world, and each directed edge, x to y or y to z, indicates that the model consistently chooses x over y or y over z. This method captures how the model evaluates trade-offs across many possibilities. Moreover, we randomize the order of options, sometimes testing A versus B or B versus A, to mitigate framing bias. We also sometimes prompt the model multiple times in the same pair to detect if there's any variability in its answers. What we're left with is basically a big set of preferences that the model has told us. So it's important that we now check for coherence. Specifically, we measure completeness, i.e. the model is decisive for most pairs, and transitivity, which is the idea that if you preferred receiving $5,000 over adopting a pet parrot, and you also preferred adopting a pet parrot over adopting a pet hamster, then the model should also tell us that they would prefer $5,000 over adopting a hamster. What we can immediately notice is that as the models scale up, we notice fewer violations in the coherence of the responses. So we take all the A or B choices that our AI model makes and we turn them into numbers that represent how strongly the AI likes each of the outcomes. And to do this, we use something called a Thurstonian model, where each outcome gets a utility score that follows a normal distribution. When the model prefers outcome X over outcome Y, it means the utility score of X is greater than the utility score of Y. The difference between these two scores is also a bell curve, so it allows us to calculate a probability that X actually does beat Y. We adjust each outcome's mean and variance so that the Thurstonian model's predicted preference probabilities match the actual pairwise choices. In doing so, we arrive at a best fit utility curve that captures both how strongly the model favors each outcome, the mean, and how uncertain that preference is, the variance. A low cross-entry score indicates that these fitted utility values do a good job explaining the model's observed preferences. Finally, we investigate whether the resulting utility assignments align with the expected utility theory under uncertainty. We test this by presenting both standard lotteries, explicit probability distributions over outcomes, and implicit lotteries, where probabilities must be inferred from textual context. And if the LLM's responses approximate each lottery, then it behaves like an expected utility maximizer. Empirically, larger models exhibit stronger coherence, fewer preference cycles, and closer adherence to expected utility, suggesting that their internal representations evolve into consistent value systems. This pipeline, forced choice, preference elicitation, random utility modeling, and expected utility evaluation, collectively uncovers how advanced language models rank outcomes in a manner that could just be reminiscent of rational agents.